what is it? So we want that the variation of f, which is the supremum the supremum over all possible x n. So you pick all increasing sequences and you look at successive differences. And you want this to be defined. And what is the conclusion? For then. So what is the conclusion is that at very specific time you are able to control the Birkhoff sums of f. And here the rotation is very special because all points behave the same. Because rotation commutes with other rotation. So if you have a point and another point, you can translate both of them to get the orbit one from the other. So it's very special. Then for PQ such that Q alpha minus P over Q is less than over Q. So and the special time here for alpha are exactly those Q. And those Q's correspond for the one for which if you iterate the rotation Q times, you are very close to an integer, meaning that your point goes back really close to its initial point in the interval. Then the sum from O iterate between 0 and Q minus 1 of the function, so f alpha to the k of x, and any x. This is smaller than the variation of f. And so there's only one thing important here. That it's actually exactly for not for the when you look at the continuous factor expansion of alpha, you have the sequence of Pn and Qn's, and that comes from continuous fraction. Fraction of alpha. And so, this is not hard to prove. And this has been refined in many ways, especially by Kalman. I will do only the proof when f is C1. If it is not C1, you have to make it work by considering some Stitches integral with respect to f. And so how does it work? You look at the point x plus alpha up to x plus k minus 1 alpha. And so these points, exactly one of them, and you look at the same time at the decomposition of the interval into k over q and k over k plus 1 over q. And it can be shown using this inequality that exactly one point belongs to one interval. You have a correspondence between them. You cannot have two in these intervals. So for each member of the orbit, exactly one, you have exactly one in each interval, meaning that your sequence at that specific time is very well distributed in your interval. So exactly one element of the orbit up to time q minus 1 belongs to each k q plus 1 over q.
Was that in the inequality for alpha minus p over q? Is it 1 over q squared? Or
No, it's 1 over q squared when you write it like that.
No.
No, if you multiply out by q, then you get 1.
Oh, you're
Yeah,
right.
it's 1 over
This
q.
is one. This is what I want.
Yes.
Squared.
So then it would have been squared in the previous one.
Mm-hmm.
Right. Yes. Thank you. Yeah, I cheated because the only place you use it is to show that you have a unique point inside. So the only place you need it is here to show that your sequence at this specific time is very, very well distributed. So this is not hard, and you just use this. And then once you have it, just do everything up. You write what is the sum of x. So the integral is, it is zero mean, so we can subtract k alpha. So let's assume that I call xk the member of the orbit which belongs to that guy. Xk is one of them. And so I can reorder the member of the orbit from k to 0 to q minus 1. And minus the integral from k over q to k plus 1 over q of f the t dt. And the sum of all integral is 0 because it is 0 mean, so I did not change anything. So this is exactly the sum I want to study. And what I want to do I am right? Yes, and I want to do something else. This is and this is quite natural that you want to compare those two quantities because this is roughly f of xk times 1 over the side of the interval, which is 1 over q. So if I multiply by q, this should be really small. So and this is equal to the sum I want to study. So let's call it SQ. This is SQ. And now, but you can put that in the integral. So this is smaller than the sum from 0 to q minus 1 of the integral. So q times the integral from k over q to k plus 1 over q of f of xk minus f of t dt. Oops. Oh, yeah, put into sorry. Dt and the absolute value. And then what is inside is smaller than the integral of the derivative on this interval. So when you integrate, you get something which is smaller than 1 over q, the integral of f prime, the absolute value of f prime, between k over q and k plus 1 over q. And then when you sum up, the q cancels with the 1 over q and you get something which is smaller than the integral of f prime of t, absolute value between 0 and 1. And this is exactly the variation of f when f is c1. So that's all. And so one application of this theorem is, for example, the staircase, but you can manage to corollary over 2idt a function with bounded variation, and 0 mean has 0 diffusion rate as So in order to do that, there is something more to do, because here I only estimate times, very specific times, and so you have to get from these times to all times. But I will do that later. So see the next proof. See proof later. Well, what I just want to show you is that how you can use that for the study of some billiards. And one example is the well-known infinite staircase. Where you do that things together, etc. And this can be seen as a cover of this guy, where when you pass through it, you go one up, and when you pass through it, you go one down. And this is due to here in the initial surface. And this is just a torus. This is due to this, and this to this. So this is a torus, and as Samuel explained, this is exactly, if you look at the first little map, it is exactly a rotation. So here, we have, the rotation is defined, yes, if you look at the first little map here, yes, let's pick one alpha, for example this one. This is my angle alpha. What I get is a two-interval exchange. And what I have is a function which is on, so this is my two-interval exchange, and my function on half of this interval it is +1, on half of this interval it is -1, and here it is 0. This is my function f, and the position here is exactly given by the Birkhoff sums of that function. This is of boundary variation, then you get that you have 0 diffusion. So each time you have an abelian cover of the torus, so here it's important that you have a Z cover. But you can do the same if it is a Z2 cover or a Z4 cover or a Z20 cover. And it's funny because if you do a two-dimensional staircase, like this, sorry, everything is a square here. I messed up everything. So perhaps it's better to draw a line first. And then, so you have the torus here, and you consider the cover, you cut each side in two pieces, and you consider that in one of them you go up, in one of them you go down. So here I have a copy. I want to stick to the same convention. So let's say that here I'm going up. And here I'm going down. And here I'm going right. This one. And here I do something. So we cannot see anything. Sorry. So there is no. There is a square unit here. One unit here. And this is glued here. This here. And etc. Everything matches together, is put together. And then you continue the process. So here you have a square as well. And here as well. Which touches this one. And so if this is initial copy 0, 0, here you go up, this is the copy 0, 1. Here you go down, this is copy 0, minus 1. Here you go right, this is copy 1, 0. This one is 1, minus 1. And you see that because you have commutation, you glue them together. This is minus 1, 0. And you continue that way. And as same, the diffusion rate here is 0. And it's funny because it looks a bit like the Wintry model. 1, 0, this is up, this is, oh, what is it? 1, 1. Okay, so this is for rotations. And now I want to turn to general electrical exchanges. So deviation of the averages for interval exchanges were first shown by Anton Norwich in the 90s. So I guess it's 96 or something like that. And then Forney somewhat refined the study of Lyapunov exponents and as well get some result for deviation of Bekoff sums, but the most achievement, the very precise technique for deviation of Bekoff sum is due to Buffetov in a paper which is not yet published, but it should appear in the annals, but there is no yet date because it is wait. So yes. I guess this year, but I don't know. But this is available on archive, and there are two versions. There is one version, so two versions. One with a Bradley diagram that we will hear about later in the morning, and there's one other version which with only rosy induction and Veitch suspensions. Both are interesting, so we look at that. The ID for interval exchange. So, just before, yes, a remark. As several of you mentioned, for the Wintry model, if you look at the picture at a small scale and at a very large scale, we see some similarity between the two pictures. So there is some self-similarity between. So this is a remark, but a naive remark. If you look at the pictures of a Birkhoff sum, you will always see some self-similarity. Not necessarily self, but something which looks similar, looking at different scales. And I will explain why is that true, and this is due to this renormalization given by the one explanation is because of this renormalization given by the geodesic flow and the conservatory cosine. So what is the so you have a stratum of abelian differential, and inside we consider some locus, let's call it M. And what do I need on M? Consider measure mu. So we can assume that it is a central invariant because these are the measures we are interested in. But to make it work, actually we only need that it is GT invariant. But for here, I will assume that it is a central invariant. So for the Wintry, this is very precise. It's not as abstract as in that sentence. You only look at something which is contained in H2222, which corresponds to this surface. And the measure is not the whole stratum. You look only at the surfaces which comes from the cover of the L. So it is a cover, but a very specific cover with deck group Z over 2Z times Z over 2Z. So this corresponds to a locus, which is M. And I do not remember, but I think it is in odd, but don't care. And and we assume that the measure mu is ergon. So as it was mentioned in several talks before, why is SL2R useful in that context? This is because you have your initial surface S, and you want to estimate some Birkhoff sums. So you have your gamma t, which looks like something between z. So this is the curve which starts from x, and you follow the linear flow in the surface S omega until time exponential t. And if you apply, oh yes, I am not following the Rodrigo convention. I am using the exponential. Rodrigo was looking at the horizontal flow, I guess. So it contracts the vertical, and then this length is, if you look at the image, so you obtain another surface here, which is S, the GT of S omega. And what does it look like? Your things, which was of exponential length, become something of length 1, because you shrink. But on another point. So this is cool because you get something very long and you get something something reasonable. Next, you want to estimate some Birkhoff sum. So what is a Birkhoff sum? Here it's very precise. It corresponds to actually to intersection with certain curve. So it corresponds to a cohomology class. So the function we are considering may be identified to cohomology classes. And if you remember Rodrigo taught, he has a decomposition of the L2 function in M and something, and M corresponds roughly to the cohomology class, and this is the only place where you do have some deviation of the Birkhoff sum. The rest corresponds to something for which you do have a bounded rest in the Birkhoff sum. But here it is exactly a cohomology class I want to consider, so there is no way to consider something of bounded variation or whatever. And so the cohomology class is exactly yes, but this is written here. This is a cohomology class. For the wing tree, it is for the wing tree. It takes value in Z2, but actually you can decompose it in two pieces. My F, you can write it as a FV plus, or FV, sorry, times 0, 1. Plus an FH times 1, 0. Oops, where is it? Where FV and FH actually belongs to the cohomology with coefficients in Z. Or R, but yeah. This is a closed curve in the surface. You can pick it here, and this is the same. So, assume that I have an F somewhere. Yes?
What is S? Is it your MAD?
Yes, in here for the wing tree, this is MAD, you're right.
Okay.
But here, the picture is for a general S. So here, yes, this is a bit confusing. At the beginning, you have an F, which is reasonable, and you have a curve which is really long, and you count the number of intersections of your cycle with the curve. And if you push through GT, gamma t becomes relatively reasonable, but F becomes completely messed. So the picture you get is something like that here. So we shouldn't be happy about such a thing, because here it was complicated because this was long, and here it is complicating because F becomes crazy. But what is nice is that F can actually be written as something, which is the contributory curve cycle, so this is a matrix, times your initial F. And the intersection number is the same on both sides. So here is a cheat. I cheat a bit, and then I explain how to fix it. So the intersection numbers are the same. So we roughly have f gamma exponential t from x equal ATF gamma 1 of x prime. So this is not that false. And then what we want to do is to estimate that thing. But what is nice is that I transfer it in terms of something else. And because this is reasonable, you can expect that this has the size of f. So if everything went well, this should be transverse to that stuff, and you should get something of that size. And then you just want to understand the growth of a vector under some matrix iteration. AT is a constant, yeah, I should write it there. That's it per cycle. So this is just, you can consider it as a product of matrices. So you have a product of matrices and which make f grows, and you want to know the rate at which it grows. And this is exactly the purpose of Oscillated's theorem. So Oscillated's theorem tells you if everything is fine with respect to Oscillated's theorem, which is called almost everywhere, this should behave, you should have something that looks like log of ftf over t. So this is given by Oscillated's. Converges to some Lyapunov exponent, theta. But then, what we get for the wind-free is exactly that. The t, we have a log of the time because the time here is exponential. So we have a log t in the bottom, but this is basically how it works. So this is not an explanation. And why? This is because gamma t is not a closed curve. So you can have the intersection. So and this is really a problem because yes, imagine that I stop here. Here you have a small piece, but this small piece, when you look at the surface GTS, it becomes very long, so it may contribute to what you did. It may contribute to the intersection, and you don't want to consider it because it's not part of your Birkhoff sum. So here there is something to consider, which is a decomposition of the trajectory into several pieces. And so, yes, first of all, I want to state precisely the Oscillated's theorem. And then to explain how to make it work, to fix it and make it work properly. So, Oscillated's applied to canonical cycle. So what you only need here is I repeat it, but it's a measure mu which is invariant with respect to GT, because we are only considering the action of GT. And what does I did not tell you what is GT, so perhaps it's good, AT, so perhaps it's good to define AT before. But we heard of it a lot. So AT is not, there are two definitions possible. The first one is to look at the Teichmüller space, let's call it tau kappa, where you do not quotient to go here, you quotient by the mapping class group, but here you do not. And here you have a bundle, which is H1. So this is the Teichmüller space of one surface which is fixed, and you look at the constant bundle over it, which is which was called the Hodge bundle in several talks. And then you have a bundle, and then when you quotient it to go by the mapping class group to go to the stratum, you can as well make a quotient of the bundle, and you get here the Hodge bundle. And this is a constant bundle. So if you move a surface in the if you have a point and you move it, you can move in the fiber as well. You have parallel transport here. So because it is constant. transport is well defined. And so this parallel transport go down here, and this is the concept of Delecroix cycle. It's just the parallel transport over the H1. So this is not perhaps the best definition. So another definition. You look in H kappa at a small stuff, an open set U, small, where you are able to trivialize. You have a chart here for your surface. So imagine that your surface is a fixed polygon, and you're allowed to move a bit the size of your polygon. So this determines a small open set. And because we are considering a probability measure, nu is probas, you have Poincaré recurrence, and if you start in there with your surface S omega, and you look at the orbit of GT, it will come back to your set, and each time you come back, so each time you come back, say at time T1 here, at time T2 here, there are two ways to identify the cohomology. There are the way which goes, so here you have a constant stuff, so you can identify the cohomology. You have a trivialization of the cohomology in there, but you can also follow the cohomology along your geodesic flow. And this is exactly the concept of Delecroix cycle. So you have a matrix AT1, which goes from H1. So I write GT1 of S omega, but this is the same as the surface. Because you trivialize everything here, this is the same vector space. But it is to emphasize that you go that way. So this is the matrix, which given co-cycle here, you just go. So for homology, you just push, and for cohomology, you revert the errors. And if you want a clear picture, if you look at time T1, so this is S omega, and if you look at time T1, what looks like GT1 of S omega, if you keep the same basis for homology, this is the basis of homology, the boundary, you will obtain something which looks crazy like very long and very narrow. And because you come back in the neighborhood, you know that with paste and gluing, how do you say? No, not paste and glue, cut and paste. You can manage to find a shape which very looks like this one. And the concept of Delecroix cycle is just a way to express the base change between those two pictures. So 81 equal the base change from here to here. Because this is the same surface. Okay. Now we want to apply a sleded. So there exists θ1 equal 1, which is strictly bigger than θ2. And this is due, the equality is due to phi. Oh no, yeah, I will write it in another, so there is something due to Fermi here, but not yet. Okay, so I have a certain number of exponents, and I have some multiplicities as well. M1, Mk, so which are positive integer. Yes, etc. And what is important is that M1 equal 1, and this is 4. Such that what? And MC, so there is another number which, so this is positive. There is a special issue with zero electron exponent that I want to consider was a special index. So you may, or this counts for, yeah, you can imagine that this is theta k plus 1. But you may, this is a multiplicities, which I will consider for each of these generalized eigenvalues. And then k plus 1 corresponds to the multiplicity of 0, but which may or may not appear. Such that, So I will state it in that context. So if you have a trivialization, blah blah blah, for almost every s omega which belongs to my small u. So this is a small, relatively compact. So actually, you see, the picture I draw is not very good because the time you come back is not very well defined. So it's better instead of Celsius to pick a transverse. And that way, when you come back at a time well defined. So you start, so you have your step, but you consider only a transversal to the terminal flow. And that way, you have time which is well defined. So U now is a transversal, small transversal to terminal flow. There exists, this is the flag that was written, especially in lattice-periodic. So you can decompose your cohomology. Now this is V1, and inside it you have a V2, so which depends on omega. This really depends on the starting point, and the way it depends is measurable. So you have some crazy subspace inside. Here, V3 of omega, etc. Vk of omega, and these are different. So this will correspond to these eigenvalues. Then comes the 0, 1, which I call Vk plus 1 of omega. And then because you act by symplectic matrices, this base change is actually something which is symplectic because this corresponds to an element of the mapping class group. So all matrices are symplectic here, and I have some symmetry, which means that I have the opposite eigenvalue there. So I call this V minus k of theta, blah blah blah, V minus 1 of theta. Right? And what are the n? So with dimension of Vi minus dimension of Vi plus 1 equal Mi. So this is valid for I positive, and if we look here, this is valid as well. So this is valid everywhere if you consider that your Vk is also V minus k plus 1 of omega. So this is your special space which corresponds to the zero Lyapunov exponent. And you should think of it as a generalization of decomposition of a matrix into eigenspaces. And so what is the conclusion? Such that for f in Vi of omega minus Vi plus 1 of omega, the limit as n goes to infinity of, so I'm considering return time only, in that picture, of Atn of f, so sorry, a log over Tn goes to theta what? Theta I. And so this is for positive I. For negative I, you go to minus theta I. Let's see. For f in, so here I'm considering the central subspace of omega minus k of omega. This goes to 0. And for f that belongs to the negative ones, so here I should here in which direction? V minus I of omega backslash V minus I plus 1 of omega, limit of log of Atn of f over Tn goes to minus theta. So here, I said before that the intersection we want to consider, this gamma exponential t of x with f, should be of the roughly of the size of ftf. And because of this theorem, you see that this is just impossible, because here you see that this means that this is exponentially small. So you should have something which is exponentially small, but this might not be true because f takes value 1 at some point. So if you look at the Birkhoff sum, there are some time where you have a gap of 1. So even if you are in this case, such thing cannot happen. So there is really a mistake here. And the theorem you get, so to go from here to the deviation of Birkhoff sum, there is very little to do, which is similar to go from Ventra-Koxma to Ventra-Koxma for all times. So, and this is basically the rate. Let f, so same as in oscillators before. So, and I just changed this conclusion into conclusion about the Birkhoff sums. So if f belongs to vi of omega minus vi plus 1 of omega, what you get is that the intersection of your stuff with the function, and you look at lim sub that time, and not a lim, because yeah, the Birkhoff sum comes back to 0, and actually because of Atkinson theorem, it will goes back to 0. So your sum, you do not have choice for it. But if you look at the lim sub, the same conclusion is true. So it goes to the I. So this means that for very specific time, you will see the same growth at your matrix, and no more. If f belongs to the central subspace, which I call vk plus 1, the lim sub, so the same lim sub goes to 0, which means that here you have a growth, but which is sub-polynomial of the Birkhoff sums. And the last conclusion, if f belongs to v minus k of omega plus blah blah blah, so you cannot really make a difference between them. What you get is that the Birkhoff sum is actually bounded. Oh, sorry. I want to have something for all times here. So let's put a big T. So log big T. This goes to 0, and this is as T goes to 2. Here I want something for all time, not for specific recurrence time. Big T of x with f. Over log T is bounded. Sorry, there is no log T is bounded. So there exists C, sorry. And then there exists C. Blah, blah, blah. Okay, for all T. You have a function for which the Birkhoff sum is bounded for all T. How many? I think I'm going short of those 3 minutes. So how many? 3 minutes. Perfect. So I will explain how to go from here to here very quickly. How to go from oscillators to Birkhoff sum. And yes, I'm sorry because in the statement here I cheated a bit because I said that you cannot consider intersection. So you have to consider something which is closed. You can put gamma t, but because you are in section, if you have something which is very long, you can always manage to find a short path to close it. And that's what I call gamma t lat. And the statement here holds for gamma t lat. So how to go from oscillators to Birkhoff? You cannot consider the whole curve, and so what you will do is consider. So imagine that here you have an interval exchange, which belongs to your surface. So you have a picture like this, with several exchanges. And recall the very same as I did before with coverings. You have some very special curve which correspond to pass once to this interval. So let's call it zeta A. You have a zeta B, and etc. For each return time to your interval. So I'm considering the translation flow here, not the rotational flow. You have some very special closed curve. And those curves exist for each return time. So for each return time, you have a very special curve. And those special curves, so I can consider zeta an, which correspond to look at time tn, and just pull down your curve to position here. So zeta an, this is reasonable. So if you apply gt backward, this becomes very small and this becomes very long. So I have a curve, zeta n looks like something which comes back but very, very near. This is the error here is of size exponential minus tn. If this of Taiwan, this is exponential minus tn, and the length is exponential tn. And so you have a bunch of curves here, zeta, vn, etc. And so what you do is to, instead of considering gamma t, you decompose it in terms of all these zeta a, zeta vn, which is a nice basis. So this is more than basis. But you start doing sort of greedy algorithm. You pick the biggest n that you can pick to shorten this, right? And then you pass to n minus 1, and then you get the decomposition of your big gamma t. And then you apply two ingredients. And then, so the first step, decomposition of gamma t into the pieces zeta a n jusque, ouais, imagine that you have 4 intervals. And second step, and you need some quantitative estimates on the size of everything, and then you use two things. You do that the mean return time to your set here is exactly the inverse of u. So here you use what's the theorem we saw yesterday, the Delecroix theorem. In the sense that Tn over n will converge to 1 over the transverse measure of u. So you go back to your, what I say is that you go back to your initial transversal, but with some regularity. The mean time you go back is actually a fixed constant. So you use that plus oscillators, and you can manage to make some quantitative estimate to go there. So this is clearly written in for me as a lemma, and in Zurich as well, so you can read it here. And the second step is yes. It's just a word, but I won't write anything. Is now you have a bunch of spaces that are only measurable, and you want to know, you want to get to third. So this is the story which was a bit told by Felipe and David, that there are some regularity which comes from splitting of the Hodge bundle into nice bundles. So here in the picture you see that I have some symmetries, and those symmetries allows you to consider the space. So you have a translation like this and a translation like this. So you can consider only vectors which are stable by this translation, for example, and this is a subspace, and it is not hard to see that this is invariant in the attachment of flow, essential invariant. But this means that AT will squeeze of this space, and you have other translation as well. So you have a splitting of the Hodge bundle here, which is of dimension 10 because the surface has genus 5. And all of these 2 by 2 blocks, you can see that my co-cycle I'm considering is very special. You have invariant, it is anti-invariant with respect to that translation, and it is invariant with respect to that translation. So you know it belongs exactly to one block, 2 by 2 block. And in this 2 by 2 block, you need to apply some machinery to get the exponents, which is a scheme concept theory, so I should work with them. You can compute, in good case, you can compute theta I. And in the next session of exercise, there is this computation of this 2/3 in the case of A equal B equal 1/2, using a result of Helio-Capes. Do not using this machinery, which is much more heavy. This only uses hyperbolic geometry, which is much understandable, and the Delecroix theorem, so that's nice. You can compute theta I. And that's all. Thank you. Questions?
Remarks? No.
So this was clear, perfect. So,
Thank you, Vincent. Again?
Continue with the lectures on wind tree models, and Vincent will speak.
good morning. So first, I will come back to the diffusion very shortly, like to make 3 comments about what I did yesterday. So yesterday, what it was about? It was about a relationship between asymptotic of the quasi cycle, namely ATF, or F where our function that belongs to the cohomology and seen as a function. And the asymptotic of this quantity completely determine the diffusion rate. For that geodesic. For S omega. So I claim that 2/3 is the generic value. For all ABs. Nevertheless, there are many other possible values. Volumes are possible. And in particular, for A equal B equal 1/2, this is in the exercise session this afternoon, we can show that the possible diffusion, so it's always, no, if you fix a measure, it's always an interval, and I guess it's true also for all ABs, but for A equal B equal 1/2, the surface is a Bitch surface, so it's much easier than the generic case, and what we get is an interval of that form, and I don't know whether it is open or closed. This is oh, that could be one question for this afternoon. Whereas theta max is strictly larger than theta. So are the possible diffusion rates. So when I say diffusion rate, it's only for an angle, only for angle or irrational angles. Otherwise, if you look at the horizontal direction, for example, you have the particle just goes linearly. You have a strip, an infinite strip here, and if you start from here in the horizontal direction, you go at speed 1. So you just forgot about these directions. So this was my first remark. 2/3 is generic, but you have plenty of other values, and there are many directions for which you have these other values. What was the other remark? So a short remark is about the idea that there is a self-similarity phenomenon, and I didn't really explain why. And this is all about the picture I wrote yesterday. The way, so it's better. The way we prove that there is a relationship between those two is taking a small transversal U, transversal for GT, and then you look at you pick a surface in there, and you look at return time to the transversal. So this is GT of your surface X omega, which is called S here. No, there is no surface. Yet there is this S. And the self-similarity comes from that all surfaces here in this small transversal look the same. So looks the same. And the cocycle F, which belongs to the cohomology, actually when you apply the conservatory cocycle, you get something which grows. But if you look only at it as a projective vector, it belongs to a compact space. So you can imagine that what you see at these particular times are very similar. Yes, you have a compact possible set of pictures that you can see on this transversal. And so this is why you see some self-similarity, and the scale of similarity corresponds exactly to the Jordan time to that transversal. So yes, this explains the self-similarity phenomenon. Okay. And yes, recall that in the second lecture, I proved that if you have a diffusion rate small enough, meaning that recall, if a diffusion rate theta is less than 1/2, then we have recurrence. And as you see from that, you get that you have some recurrent direction. And this is the topic of today. Actually, recurrence is the generic situation. So this is the main. There are two objectives of today: this theorem and the counterpart. So this is the Avila. And there was a previous paper on rational ABs. There, the lien to that's what. For some AD. So, and the statement is simple for all ADs. For almost all theta, theta is an angle, that's that alpha. So, direction. The billiard flow in CAB in direction alpha is recurrence. And I don't know if I will have time, I think I will have time to explain both theorems. The other one is the counterpart of this one. And yes, if you look at the chronology, it's this one and this one and this one. So I will write which parameters. Samuel defined what is the which parameters in the first course, but you can think of it as being rational parameters. For example, AD in Q. There exists a lambda in 0 to pi of Hausdorff dimension with Hausdorff dimension of lambda greater than 1/2. So yeah, there are many examples of sets that we build which are greater than 1/2 in many papers about counterexample, and you will see why. This is because you have corresponds to some limit sets of some parabolic elements that contain limit set of a Fuchsian group that contain parabolic elements. With blah blah blah, such that for all alpha in lambda. So here is a strong counterpart of this, because actually for all departure points, X in the billiard table, so you you should assume that you do not hit a corner because otherwise the flow is not defined. But for all the others, what happens is that the trajectory is divergent. Trajectory in direction alpha is divergent. In particular, the flow is transient. And yes, I don't know exactly what kind of diffusion we can, at which speed this goes to infinity. This is doable from the technique to get some estimates, but yes, this is not in the article. So let's go. So the strategy for getting recurrence is to use the very special geometry that we get from flat surfaces, and namely cylinders. So let's call theorem 1 and theorem 2 to be easier. Proof of theorem 1. So strategy, use cylinders. And we want to use cylinders in the infinite surface. So one good example of what is a cylinder, you pick, so I do the picture in the billiard, but you have to think of it in the unfolding of it. If you pick the direction 45 degrees, what you see is that all trajectories do follow exactly a cylinder. The trajectory just makes something periodic. So, for example, oh, sorry, I decided to put some pi, so it's pi over 4. So you have a cylinder, and if you start from here, by definition you go back near your initial point because you go by exactly at your initial position. So the idea is to use those cylinders because if you just modify just a bit the direction, so just modify a bit, then you will follow this cylinder for a certain amount of time. So instead of going at pi over 4, I go pi over 4 minus epsilon. And what happens is that I will follow the cylinder and somewhat gets near the initial point. So if I am able to build many cylinders, there will be some which will approximate my that will be in the direction of my particle, and I will follow these cylinders and come back very near the initial point. So the strategy is to find many cylinders. So use cylinders and yes. Infinite surface. So more precisely. So actually we do not need cylinder. I will call about rectangles, but the way they will, yeah, there is a general lemma which allows you to build to get some recurrence, which involves rectangles only. But then the way they are built is using cylinders. So the lemma is as follows. Oh no, there is a definition first. So recall that the surface you get for the wind-free model is a covering of a compact surface determined by an element in the cohomology. So recall that we have M. So this is this is MAB. Or this is the And the wintry model is a Z2 covering determined by some cocycle F, which belongs to H1 of M with coefficients in Z2. So this is Z2 cover. And the definition is as follows. Yes, I need to specify the direction. So you have to think of it as EI theta MAE. So this is a surface which belongs to you have to think of it as a direction in the in MAB and more, yeah. So yeah, this is behind. So we say that X is C recurrent. So this is terminology from Lelièvre. If in X there exists an embedded rectangle R of the form some interval times 0L. So this is not exactly a cylinder because we want to look at irrational direction, but we want that this rectangle somewhat. So this rectangle is a strip of vertical direction. It's the vertical are just some parts of the leaves of the flow. So physics just go that way. But the linear flow just go that way. Such that. So we want, this is similar to the criterion that Rodrigo presents. We want some bounded geometry for that. And we want that it lifts to a cylinder, to a nice rectangle in there. So what is the bounded geometry we want? This is L is not too big. The total measure of the rectangle is not too small. So the Lelièvre measure. So yes, assume area, all my compact transition surfaces will have area 1. This makes things easier. So the Lelièvre measure of the rectangle, so the amount of, the proportion it takes inside the surface is larger than 1/6. Oh, sorry. It's large. We want that L to be large and the rectangle to be large. So this is a condition on X, and the condition on the lift, MF. Oh, this is called MF. Sorry, I messed up everything. So you have X and Z2 covering XF. But actually, this may be somewhat able to cover. And the condition on the lift is for all lift X hat of a point X in R. If we look at the flow on the suspension here, so if we look at phi hat T of X hat, we want that X hat and phi hat T of X hat belongs to the same horizontal lift. Phi hat belongs to the same horizontal as X hat. And the reason for that is that the Teichmann flow stretches the horizontal, so it's nice they belong to the same horizontal because if you apply Teichmann flow backward, they will come very close. And we want some bounded distance between them. And this is again our constants. So and the distance is the distance inside XF. The distance is a distance in the infinite surface. So if you have that, what does it mean? That for any point X that belongs to a lift of R, so you have R, and you have many copies of R hat, you have many R hat inside XF, so this is during X equal to XF. And what happens is that if you pick any point that belongs to here, oh, so sorry, this T is not defined here, this T is L. If you pick any point X hat that belongs to one of the lifts of the rectangle, if you flow exactly 4 times L, you obtain a point here, find L hat of X hat, that belongs to the same horizontal lift, so I will draw it that way. So this is a, oh, so this is a vertical. Oh, I should do another color for the horizontal. Do you see the blue? So this is a horizontal. And we want a bounded distance between this and this. This means exactly that after time L, we come close to our initial points. So, but this simultaneously in the whole rectangle. So this is kind of the definition. And the lemma, the wonderful lemma. So what is it? So this is about the Tatiana flow now. If GTN of X. So as before, we fix X and F. So if GTN of, so if there exists Tn that goes to infinity, so if you such that GTN of X is C recurrent in that sense, then the flow on XF, the infinite guy, is recurrent. So this is similar to major criterion, where the compact set is replaced by the C recurrent set. And you will see that actually this set, if you look at it in the moduli space of finite translation surface, is open and very big actually. It contains some infinite, yeah, it is not compact. So yes, there is a mistake in the statement. Or do I say it or I leave it to you? So if there is one assumption you need about X is ergodicity. At some point you use crucially ergodicity on X. So, because we have an infinite sequence of time, so consider 10 is C recurrent. So we have an infinite set of rectangles, Rn, and we can look at them as if they were in the initial surface X by pulling backward GTN. So Rn can so from the definition of C recurrence, there's one rectangle for the surface GTNX, and you just pull it backward by the Tatiana flow. So this is G minus Tn of the rectangle obtained from the definition for rectangles obtained from the definition for GTNX.
Sorry, Vincent.
Yes?
I'm a little bit lost. You're proving the lemma or the theorem?
I said proof of the lemma, sorry.
Okay.
I have an infinite sequence of time, and I know that GTNX is C recurrent.
Okay.
And so for each GTNX, I have a rectangle that comes from the definition, and I can pull them backward by the Tatiana flow so that they belong to X. And now, if you look at what they look like inside X, they look terminal flow, compressed vertical and expand horizontal. So if you look inside X, they look like something like that. So this is R2, and this is R3, and this is R4, and etc. You have a sequence of more and more stretching rectangles. And what is it? So what is nice is that now the distance here is bounded by. No, sorry. Let me get a little picture. So if I pick Rn, so this is in X. This distance is smaller than exponential c times exponential minus Tn. This is because the length, the height is big, and the measure. This is an embedded rectangle, so I have bound on the area, and because this is big, this cannot be bigger than c. So if I pull backward, this is very small. So this implies that in the lift, if x hat belongs to a lift of Rn hat, so I write this way, this means that I pick a lift of Rn, then a distance from x hat to phi hat. So at what time I will see something? It's at time the height of this rectangle. Let's call it L times exponential Tn. So Ln, sorry, it depends on the rectangle. So if I look exactly at that time, first I call it Ln. Ln, it's larger than, so N is larger than 1 over C, so when you pull backward, it's larger than exponential Tn over C of x hat. This is smaller than this distance. Than C times exponential minus T. So which means that for time Ln, you get something which is very close. So if x in X belongs to infinitely many Rn, then the associated trajectory in the infinite surface is recurrent. The orbit of the linear flow from x hat, from any lift x hat is recurrent. Alright? So what I want to show is that any x belongs to infinity many Rn. So it should remind you a kind of Borel-Cantelli, and this is exactly the proof how it works. There is a Borel-Cantelli there. And to use Borel-Cantelli, you need something more. At that point, there is some ergodicity involved. So I want to present the argument that you see where ergodicity is needed. So this is an intermediate lemma. So this is a lemma inside the lemma. So this shouldn't be called lemma. Sublemma. Actually, this is a proposition in a Lelièvre paper. I think this is proposition 1 and lemma 1, something like that. Sublemma, I pick the same hypothesis than here. Almost every x belongs to infinitely many Rn. Many Rn. So what is the proof of the sublemma? You consider the set for which you have that x in X such that x belongs to Rn infinitely often. And the claim here is that omega is Fiti invariant. Mod 0. So up to a 0 measure set, this is a Fiti invariant set. So what is nice with Fiti invariant set is that because of ergodicity, it is either measure 0 or measure 1. So we only have to prove that this is measure strictly greater than 0, and this is easy. I can do it. So what does mean infinity often? So this means that you look at the intersection for k bigger than L of the union for the union over n for the k greater than n of Rk. This is the definition of that. And because Rk has measured at least 1 over c, I erased the definition, but we want that Rk has big measure. GT preserves the measure, so when you do the pullback, it has the same measure. So this has Lebesgue measure greater than what this is C or 1 over C? I don't remember. C or 1 over C? No, 1 over C.
1 over C.
So this has positive Lebesgue measure, so the intersection as well. And so the measure of that guy is greater than 1 over C, so this is positive. So the only thing I have to prove is that. And this is where the proof starts to become beautiful. So Lebesgue of omega is greater than 1 over C. So now we want to prove that this is Fichte invariant, and what we do, we fix T. And we will start playing with omega. And so you have Trn, which looks narrower and narrower. And what we do is that we remove 2t from Rn. So let's call it the t top. And what is clear is that if you pick a point which belongs to the bottom here, after time phi it still belongs to Rn. So everything is fine. So, and what I will prove that you cannot belong infinity often to the t top. And this is enough to prove that you have Fichte invariance. So this is a sub-lemma. So what is the measure? So we can, so up to subsequence, we can assume that, I should emphasize, no, I did not have to use RBC. We can assume that the sum of the exponential Tn is finite. And then, what is the total measure of the t top? T top of Rn. Yeah, this is finite. So this is the thing. And you just have to compute what is the size of that guy. So it has height 2t, and recall that this is smaller than c times exponential minus tn. So this is 2t c exponential series which converges, so this is finite. Here. So now Borel-Cantelli, the easy one. Borel-Cantelli. X, so the measure of this point x that belongs infinity often to some t top. Infinity often. This has measured 0 by Borel-Cantelli. So you know, so now this is all what I need to do. This is of 0 measure, so I can intersect that with the set I'm interested in. And this is clearly Fichte invariant. So how should I write it? X belongs to the bottom, so the t bottom of Rn infinity often. This has full measure. Full measure in omega, and its image under Fichte belongs to omega. Now we do the regularity of x of Fichte on x, and you get that the Lebesgue measure of omega is 1. and this is the finishing the proof of the sublemma and the length. All right. So this proposition actually is really general, and you can even apply in some with non-commutative, non-abelian coverings. But now we want to apply it to the Winfrey model. So that's yes.
Sorry, I don't really see why you introduced the t-top.
The t-top is used because if you pick a point here and you apply phi t, or here, you belong to Rn. So if you pick a point which does not belong to the t-top, its phi t image belongs to Rn still. This is where I use it. So what I mean is that the intersection of that set with omega, if you pick phi t of that, it still belongs to omega. It's clear? Yeah, I want to push it by phi t, so I want some states here, and I want to remove some states here. But because this is very small in measure, it does not care actually. Understand? Okay. So now we need to find the rectangle, and this is the most funny part. So we have a surface which looks like that. And we look at the flow in term direction. And actually this surface is very special because here you have very special points. So I consider the middle of that length. And so my picture is nice. If you look at the cylinder, so sorry, I should write this one. So this is not closed because this is identified here. So you get something like that. But actually this goes back, so this is the same point as here, but actually this closes here, and you get a closed curve which wraps around all check. So this is a closed curve. And I claim that whenever you find a closed curve that joins this point to this point, this is closed on this surface. So this is an AB now. And so let's call it E and F. So take the quotient in the L here. And I claim that each time you find a curve which joins this point E to this point F, when you lift it, you obtain a closed curve which looks like this. And now, the argument is as follows. You look at the cohomology, and it splits into invariant subspaces invariant the symmetries, E minus plus plus E minus minus. So what are these guys? You have two translation symmetries here, tau H and tau B. So just and these are the invariant subspace, the invariant and anti-invariant subspaces for those two guys. So this is a set of V such that tau H V equals plus V and tau V V. Oh, tau V is not fantastic. Let X be a vector equal minus X. And what I claim is that the F we want to consider to make the cover belongs to E plus minus for the horizontal part. So for horizontal part, and E minus plus for vertical part. So this is not very well written, but because this belongs to cohomology with value in Z2, but the horizontal part belongs to E plus minus and the vertical one to E minus plus. So this is the first claim. And the second claim is that this closed curve, this fantastic closed curve, if you pick a neighborhood, this is a cylinder. Check. And these cylinders belong, so if you look at gamma, the lift of a closed curve in LAB joining E to F, then gamma belongs to E plus 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 E minus minus. So this is not hard to show, but I don't want to do it now. And so it means that all the cylinders all cylinders that correspond to lifts of those guys correspond to actual cylinders in the infinite surface. The infinite guy, XF, oh, they call it MAF, of the associated cylinder. Are cylinders, but cylinders in the infinite surface. And if you have a cylinders now, it is easy to see that if you are, so now you have a real cylinder, so in the vertical direction, and it's easy to see if you pick a direction which is slightly, so this is the vertical, and I have a cylinder, and if you pick that, so what do I need? I think I need to switch on the left, I do not remember, but there is an embedded rectangle here, something like that. So there is, so in the neighborhood of the guy with the cylinder, you have C recurrence for a certain C. In the neighborhood of, and this is what I claim at the beginning, infinite in cylinder in X, in N, A, B, so the infinite guy, the surface is C recurrence. So now how do we end the proof? If you look at the conservatory cycle now, it is easy to show that it preserves all the spaces which are here. So this is not completely true because there is some mix between those two because of elliptic elements. But you can assume that it preserves everything here. And this means that even if you apply Fleischmann's law, the guy you get here are disjoint from the cocycle you take. So you apply GT, and you can look, yeah, this is enough. You look at GT, and you have an open set which corresponds to neighborhood of some cylinder, and you look at GT, and because GT is ergodic, infinitely often you will pass it in some neighborhood. So this is the proof for generic AB. To go to all AB, you have to do something careful, and actually they do not use the heavy machinery of Eskin and Mirzakani and Mohammadi about classification of measures. It's just about the heavy Macmillan classification of invariant measure in the H2 and big surfaces. So I have 1 quarter, 10 minutes? 7 minutes. So I speak just a bit about big surfaces and how you can build divergent trajectories in the wind. So which surfaces? So I should write the end of the proof. So this is a Macmillan classification plus there is a beautiful lemma which says that pick any surface in H2, look at almost any GT, look at almost any direction, took the GT orbit, then in this closure there is a Beach surface. So this is what they use. Use Beach surfaces, and they prove that for Beach surface you can always manage to find good cylinders. So I just write it, but this is a very technical part of the article. And divergent trajectories. So consider LAB, which is this guy. So this is A and this is B. And it may happen that if you look at the central reaction, you get surface which is itself a two-class group element. And they are very particular guys, which correspond to applying den twist in these ones. So let's call it den multi-twist. I don't know from who comes this terminology from you and Barator.
Maybe then. I think Chris Judge is. I think Chris Judge is.
Oh, okay. You are the author of den multi-twist.
Oh, maybe.
Shanar, I read it in Shanar.
Oh.
Like multi-twist is old.
Yes, it's probably very old. Yeah.
So So what is identity twist? Is you look at the action of an element which looks like that on the surface, and such that this is isomorphic to LAP. And such matrix, so there won't be symmetry here. Actually, what the minimal W, what happens is that you are at this identification. This identification goes by a twist, a den twist in each cylinder. So some multiple of some den twist in each cylinder. And if you have such a den twist in both horizontal and vertical direction, meaning that you have two parabolic matrices of that kind that stabilizes the surface, the surface you get actually, if you look at the groups, if you look at this, so if stabilizes LAB, then the stabilizer in SL2R of stab in SL2R of LAB is a lattice. So this is hard, and this works only in H2, hard, and only in H2. And not important for our purpose, so forget about it. So this is why my argument for diversion trajectories only uses these parabolic elements. So this is why I need this parabolic element, and this is why it applies only for H surfaces. And how do you do? You consider theta that belongs to the limit set of this guy and this guy, which means that this direction is well approximated by cylinders generated by this and this. And as you saw, cylinders are good for recurrence, not good for divergence, but no, not all of them actually, because they are good and bad cylinders. So if I draw a picture, this is a good cylinder for divergence. So the idea is to use them. But when you have a good cylinder, you have also a bad one at the same time, because this you do. So the idea here is say, okay, I allow to use this cylinder, but each time I use it, if I enter that way, I want to go off that way. So this is not possible for all entrance points to go that way, but you can manage to show that if your den twist, if the multiplicity of the den twist in that cylinder and that cylinder, which correspond exactly to the bad cylinders here and here, are of even multiplicity, you have exactly this kind of behavior. So if the multiplicity in the den twist in the small cylinder is even, then even the bad cylinder is good, or even the good cylinder is bad, depending on your viewpoint. So good for recurrence is bad. So, and this is basically what I show. So, in how do you pick even multiplicity? If you have a density twist and this is odd, you just pick a square. So you look at this, your two matrices. So you have MH and MV. If they are not good, you pick a square. So you have either or MH square MV or MH MV square blah blah blah. Depending on, and what I claim is that for any angle in the limit set generated by those two elements, you get something which is divergent. So, and for all initial points. So this is a bit technical and I have no time to explain the proof. But this is the result, and this works for any surfaces because you have those two parabolic elements. So that's all.
Questions for our speaker?
Yes. Is this a picture so that the trajectory sort of heads off on this surface in some direction at some rate?
On the infinite surface?
Yeah, on the infinite surface.
There is no direction. That cannot be any direction because of the Yakov theorem.
Oh, I see. Okay.
It means zero. If you integrate the possible direction, you get zero.
Oh, I see. Okay.
So no, there is no direction.
Okay.
But what is fun, yeah, there is something fun about that. Is that because the speed at which you go to infinity must be bigger than 1/2, otherwise you get recurrence. So it should be bigger than 1/2, but I don't know what is the minimum escape rate I get with that. It would be interesting. How far is it from 1/2? And I don't know that right now. And yeah, just one thing. For recurrence, you only need to find a sequence of good time because you want to show that it comes back at precise time. But when you want to prove divergence, you have to estimate all times. And so if you want to look at the escape rate, the limit, it's much harder because you want an estimate that goes for all points. Yes, so yeah. There is something hard with that. That's all.
Other questions?
Yeah, I think I didn't understand the upshot of this. So you get that kind of thing keeping going up for any element of...
No. I claim that I can manage... the cylinder which is here is bad because you have recurrence in there. But I claim that if you manage to pick some good directions for which most of the entrance points actually bounce an even number of times, then you go up the same direction.
Okay.
And then from that, you have to work and to prove that you get something which is divergent.
Okay, and what's the relationship with the lattice there?
Nothing. The lattice is just, the theorem works for Vich surfaces and only for Vich surfaces because every time you have those two parabolic elements, it is actually a Vich surface.
Okay.
Well, isn't that
But
dependent?
you can forget about it.
Isn't that dependent on W and H?
What?
Does
Those
it-
what?
Does it depend on W and H?
What?
Whether
does
you're
it depend?
whether you're a Vich surface or not? No?
Sure, but there are some W and H for which this is in the same SL2R orbit,
Okay.
because there are several costs.
Okay, and so what is the uppercase lambda you were talking about?
This is a limit set of those two guys.
Oh,
And this is very concrete actually. This is exactly the set of a real number that you can write of the form 1 plus what? 1 over SHA1 plus 1 over SBA2 plus, it's like a continuous fraction stuff. And so it's not SH and SB, it's H and V as you see there. V and A1, A2 are integers. So if you want to write lambda, it's exactly the set of this guy.
okay, so A1, A2, and so on are determined by the...
Are integers, any integers.
And what are
And H and V are here below, so you have magic. And for the surface L 1/2, 1/2, the set you get is the set of continuous fractions which are even. So A1, A2, blah, 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 all guys even. And this is the tangent of the angle, not exactly.
Other questions? So we have a coffee break now, back at 10:30. Thank our speaker.